Um,
Wait, so your time begins now.
Time begins now. So there were sort of two different main parts to this project, or at least that's how we split it up. There was the hardware description and simulation work, and then the actual hardware, the stick logic gates. So I covered most of the hardware description stuff. Montu did most of the hardware, and that's generally who we'll be talking about with each part. So we initially created a hardware description language to be able to simulate the behavior of our digital circuits. An HDL is basically a big long text file that looks sort of like assembly code that tells a computer exactly how different elements are laid out and connected to one another. You see them with field programmable gate arrays, which are extremely useful for high-speed electrical engineering. And they have a couple of design features. They need to be concise, they need to be extensible so you can add new components, they need to be clear because readability is important. And then the second thing to note is that an HDL isn't a very good first level design tool. It's not something you take components and start bashing stuff about and seeing what works. You design something on paper and then you go see if it works, what's its behavior, does it do what you want it to do? So all our hardware designs were done on paper first and then tested here. We architected the program in Python. Ideally, it would have been done in C or C++, but frankly, it's been years since I last used those. I didn't want to. We used objects to express logic gates and other objects to express the connections between those gates. That allowed us to basically extend different gates as we needed. Now, the simple binary operators were immediate adds, but I actually needed to go in and add, for example, monitoring gates later that would tell me what output I got from certain things. Used a master array to keep track of everything, which was not optimal, but it was fast to implement. And we set things up on a tick structure. So every time you sent the signal to the master list, it would update all the gate outputs, and then it would propagate those outputs back to the inputs, and then that would be one cycle. And then you keep doing that to simulate the behavior of the circuit. This is extremely reliable for circuits that go to a steady state, but it can cause problems when you deal with oscillating circuits. We neglected to deal with oscillating circuits though, so it ended up being an unimportant problem. And this is sort of a demonstration of the use of the program. You're defining all your gates there, defining the connections between those gates there, defining your initial probing setup, the things that are initially high or low, and then running the thing. This program describes this circuit right here. It's not a graphical interface, but it is effective in its own way.
Yep. Alrighty. So our goal of this project was trying to design logic gates using seesaws, sticks representing the seesaws, where the high represented 1 and low represented 0. So binary code consists of zeros and ones, typically corresponding to voltage. 0 would be representing 0 voltage, 1 would typically represent 5 volts. And what logic gates, the objective of logic gates is they're building blocks of these integrated circuits. Next. So, yeah. So we have to look at electronic versus these hardware implementations. Typically, some of these complicated circuits use these NAND gates, not AND gates, which are generally complex. I guess we'll go next because we're short on time. So what we mainly did was first we looked at each of these AND, or not gates, and these represent binary codes. So if I had like 0 for any, so if it's an AND gate, if there was a 0 for any input, then the output would be 0. If it was an OR gate, if there was a 1 for any input, there would be a 1 on the output. and the not would just flip your input for the output. So if we go to the next, we'll show how we've designed it. So this is the theory behind what we did with our seesaws. So we put masses. So we had like a double seesaw. We had a fulcrum, and we had two seesaws on one fulcrum, representing each input. So if we had an AND gate, what we did was because both of them had to be ones for the last one to be raised, we had the last mass, the final mass, to be greater than both the sum of both the masses of the first seesaw, but then but then of course smaller than both of these masses, but bigger than each of these masses. So that way, if I raised one of them, it would not raise the final output. But if I raised both of them, it would. For an OR gate, because only one output needs to be a 1 for the output to be 1, the final mass, the mass of the second seesaw, just has to be less than either of the masses of the double seesaw on that fulcrum for the OR gate. If we go next, of course, a NOT gate would be a simple seesaw, since we had one since it'll be input and it'll just change the opposite for output. A XOR gate or XOR gate is basically a combination of a NAND gate, two NAND gates with an OR gate. And so that's what this is trying to represent. You have an input, and each end will sort of trigger a NAND gate, which will combine with the OR gate using the same theory of the whole theory of torque that we had from the AND or the OR gates. So if we go next, and the interesting design for a circuit we decided was an order-dependent latch. This is pretty much an AND OR latch where it depends on the input in this case. And if you look at the circuit diagram, if we go to the next image, this is the circuit diagram, is how we implemented our circuit, combining this is an OR gate, but along with a NOT gate, which flips the direction of the seesaw in the middle to get the AND gate. And if you look at the very final diagram, this is using the 40 centimeter by 40 centimeter board to design a NOT our attempts of a NOT gate, an AND gate, an OR gate, a ZOR gate, and our interesting design of our circuit using this latch, which uses the theory that we have described earlier with masses and torque to properly emulate the conditions needed to get the desired outputs.
Yeah, we ended up, due to space constraints, our gates are fairly large, deciding not to try to implement the 4-bit adder. I built it in the hardware simulator. It was extremely useful in debugging it, but
unfortunately, your time is up.
just our sources left. So
gotcha.